In this video, we'll continue our discussion on Timberlake, Chapter 4, Atoms and Elements, specifically on subatomic particles. An atom is the smallest particle of an element that retains the characteristics of that element. For example, a sheet of aluminum foil contains atoms of aluminum. In this section, we'll want to describe the electrical charge of a proton, a neutron, and an electron, and identify their location within an atom. In the simplest model of an atom, we have an atom consisting of a nucleus and electrons that orbit about the nucleus. The nucleus, again, is in the center of an atom. The nucleus contains the protons and the neutrons in an atom, and the electrons are arranged around the outside in something called orbitals, and we'll talk about those later on. The protons are positively charged particles. Neutrons are uncharged particles, and electrons are negatively charged particles. Again, the protons and neutrons are found in the nucleus, or in a hard core in the center of an atom, and the electrons orbit around the nucleus in paths called orbitals. Like charges repel each other, and unlike charges attract each other in a similar way to poles in a magnet. Early chemists attempted to prove and explain the existence of atoms. Dalton was one of those early chemists, and in Dalton's atomic theory, he described atoms as tiny particles of matter. And they're also parts of an element that are similar to each other and different from those of other elements. Atoms of two or more different elements combine to form compounds, and atoms can be rearranged in these compounds to form new combinations. This occurs during a chemical reaction. Atoms are never created or destroyed during a regular chemical reaction. J. Thomson attempted to build on Dalton's atomic theory by explaining the existence of subatomic particles. Thomson realized that atoms weren't the smallest particles of matter. He realized that there were particles smaller that made up these atoms, and he proved that cathode rays were subatomic particles that contain negatively charged particles, and that they were smaller than the mass of an atom and therefore made up parts of the atom. In fact, what he did was he developed a cathode ray tube, and that might sound familiar. Older CRT monitors use this technology. And so he had a negatively charged cathode and a positively charged anode. He evacuated a chamber, meaning he drew a vacuum on the chamber and applied a voltage across the anode and the cathode, which weren't touching each other. The cathode began to emit what he called cathode rays, which was actually a beam of electrons. The cathode ray tube emitted this beam of electrons, and then he deflected this beam of electrons with magnets. And he noticed that the beam of electrons could be deflected by, he also used these charged plates, and it would be repelled by the negatively charged plate and attracted to the positively charged plate. He was able to view this with a phosphor screen. And again, this technology was used all the way up into the late 20th century with cathode ray tube televisions and monitors. So Thomson realized that subatomic particles existed and that we must have positive and negatively charged particles in an atom. He proposed what was called plum pudding model of the atom, in which electrons were randomly distributed throughout a positively charged cloud like plums in a pudding. Now, puddings at the time weren't like puddings that we think of today in the United States. They were more solid and often contained little fruits within them. So He called this a plum pudding model, and plums could be used to describe any little candied fruit or something like that. And he had negatively charged species, which he called plums, and a positively charged sphere of density around it that he called the pudding. So the plums were distributed throughout the pudding in his plum pudding model of the atom. Another chemist, Rutherford, came along who wanted to expand upon Thomson's model. And he actually tried to prove Thomson's model by developing a gold foil experiment. He used positively charged alpha particles, which were essentially a helium nucleus, and he aimed those alpha particles at a gold sheet. He expected all of the particles to just travel straight through if the plum pudding model was accurate. But what he observed was that while many of them did travel straight through, a lot of them were in fact deflected. So that proved that the atom wasn't a plum pudding type of thing. It actually had a hard, dense center, and that center had to be comprised of positive species. So again, he took his alpha particles and aimed them at a thin gold foil sheet, and a lot of the alpha particles just traveled straight through, as he expected, but many were deflected at huge angles. And so, by being deflected at these huge angles, what he discovered was these alpha particles were hitting a hard core in the atom and being deflected by that core in different directions at large angles, indicating that these atoms had a positively charged core, or what we call now a nucleus. So we arrived at the structure of an atom. An atom consists of a nucleus, which is located at the center of the atom, containing protons and neutrons, and represents most of the mass of an atom. It also has electrons that occupy a large empty space around the nucleus, and that actually takes up most of the space in the atom. The protons and neutrons make up almost all the mass, and they're packed into a tiny volume of the atom called the nucleus. Here we have a lithium atom. If we look at lithium on the periodic table, lithium is element number 3, which indicates that it has 3 protons in the nucleus. So we see here the 3 protons indicated by red spheres, and we see the neutrons indicated as blue spheres. This is an inset where the nucleus is actually here. It's very small in the center of this atom, and this atom has 3 electrons which orbit the nucleus in this large sphere of electron density. It's like a big cloud around the atom. Because the mass of subatomic particles is so small, we need units that can reflect that small mass. And so we use units called AMUs. That's one way of representing atomic mass, and this stands for atomic mass unit. One AMU has a mass equal to 1/12 of the mass of a carbon-12 atom, and carbon-12 contains 6 protons and 6 neutrons. 1 AMU is also equal to 1 Dalton in biology. Now we're going to see another way later on in the course to weigh or to measure the mass of atoms, and that's going to be in grams per mole. We're going to see that AMUs can be equated to grams per mole, so we can use those units interchangeably. We use AMUs, for example, if we're talking about a single molecule or atom, and we use grams per mole if we want to actually measure a certain amount of atoms on a scale. Electrons have such a small mass compared to protons and neutrons that their mass isn't generally calculated when you're calculating the mass of an atom. The mass of an atom can be calculated if you know how many protons and neutrons it has. So a proton has a +1 charge and has a mass of 1.007 AMUs. A neutron has a 0 charge and has a mass of 1.008 AMUs. An electron has a -1 charge and has a mass of 0.00055 AMUs. Again, the protons and neutrons are inside the nucleus and the electrons are outside the nucleus. Which of the following subatomic particles fits each of the descriptions below? Protons, neutrons, or electrons are found outside the nucleus, have a positive charge, have mass but no charge. The electrons are found outside the nucleus, the protons have a positive charge, and the neutrons have a mass but no charge. In the next section, we'll talk about atomic mass and atomic number.